Welcome, everyone. I am absolutely thrilled you're here for this explainer, because today we are tackling a massive optical mystery. If you follow display tech or optoelectronics at all, you already know that modern OLED materials are just incredibly efficient at the molecular level. I mean, they generate light almost perfectly internally. And yet, when we actually look at a glowing screen, a huge chunk of that energy is just missing. It literally vanishes before it ever reaches our eyes. So this brings us to the central detective question of this explainer. Where exactly is that missing light going? Think of it basically as an invisible optical heist. We're generating these precious photons, right? But something deep inside the device is siphoning off that energy, turning it into useless heat way before it can ever escape the screen. To solve this, we've got to look really closely at the fundamental physics happening right at the boundary of the metal electrodes. Okay, let's dive into this with a really helpful analogy. Imagine a brilliant musician playing in a room with two exits. One exit leads out to a cheering audience, but the other exit is just this intensely sound-absorbing wall. Now, if the room is built so that the sound is efficiently guided right into that absorbing wall, well, the musician could play an absolutely flawless, perfect symphony. But the audience, they're going to hear absolutely nothing. In our OLED devices, the light-emitting exciton is our musician. It releases energy beautifully. But a phenomenon called surface plasmon polariton, or SPP coupling, acts exactly like that absorbing wall. So here's our investigative roadmap to track this down. 1. The missing light mystery. 2. Anatomy of an SPP. 3. Why energy gets trapped. 4. The Purcell paradox. And 5. Defeating plasmonic loss. Section 1. The missing light mystery. Let's officially identify our culprit. So a surface plasmon polariton, or SPP, it's not just a normal photon that kind of got trapped bouncing around inside the device layers. Oh no, it's way stranger than that. It's a coupled excitation. It's this bizarre bound hybrid made of two completely distinct things. A collective oscillation of free electrons in the metal paired with a trapped electromagnetic wave in the adjacent dielectric or organic layer. It basically travels horizontally, right along the interface between those two materials. Now, what's really interesting here is how that collective electron oscillation ripples through the metal layer, paired perfectly with that evanescent electromagnetic field in the dielectric layer, which decays the further you move away from the interface. And if you look closely at the dielectric function equation for the metal, there's a crucial detail: that imaginary part, typically labeled with a double prime. That imaginary part mathematically represents optical loss. It is the direct reason why SPPs and OLEDs don't just sit there. They actively, continuously turn our precious optical energy straight into heat. Section 2. Why energy gets trapped. Let's dig into the crime scene mechanics. The answer to why it gets trapped really comes down to a fundamental momentum mismatch. If you map it out, the SPP curve sits entirely to the right of the escaping photon light line. In physics terms, for typical metal-dielectric interfaces, the in-plane wave vector of the SPP is significantly greater than the wave vector of ordinary light in the dielectric. Put simply, the SPP has way too much in-plane momentum to cross the boundary into free space and become a normal escaping photon. Unless you provide an additional momentum boost, like adding a grating or surface roughness, that energy has literally nowhere to go but into the metal to be absorbed. And this brilliantly illustrates how incredibly sensitive this trap is to distance. Because the SPP is an evanescent field, it decays exponentially as you move away from the metal interface. And since optical power depends on field intensity, moving an emitting molecule just a tiny bit closer to the metal drastically accelerates how fast it dumps energy into that plasmonic mode. Seriously, just a few nanometers can be the difference between minimal SPP loss and total optical quenching. But, distance is really only half the battle. The orientation of the emitting molecule is another massive risk factor. Surface plasmons are strictly TM polarized, meaning their electric fields oscillate perpendicularly to the metal surface. A vertical dipole has electric field lines that act basically like perfect plungers, driving energy directly and super efficiently right into those TM polarized surface waves. A horizontal dipole, on the other hand, it sits parallel to the surface and couples far less efficiently. It mostly sidesteps the trap altogether. Section 3. Diagnostics and the Purcell paradox. How do we detect this thief? First, we have to isolate the SPP from other suspects, specifically ordinary waveguide modes. This diagnostic matrix breaks it down perfectly. See, waveguiding is caused by total internal reflection within the high-index organic or glass layers. But SPP loss? That's caused by coupling directly to the metal electrons. Waveguiding can involve TE or TM modes, but SPPs are exclusively TM polarized. And crucially, while you might recover waveguide loss using macroscopic lenses or scattering layers, extracting an SPP requires sub-wavelength gratings or just entirely replacing the metal. They are distinct physical phenomena, and they demand totally different mitigation strategies. Which leads us directly to a very dangerous, albeit common, misunderstanding in optoelectronics. There's this assumption that goes, hey, if the lifetime of an exciton decreases near a metal, the emission must be getting better. And, it sounds perfectly logical, right? If it decays faster, it must be pumping out photons faster. Actually, scratch that. It's completely wrong. This is known as the Purcell paradox. The Purcell effect dictates that an optical environment changes the spontaneous emission rate of a molecule. When you place an emitter near a metal, its lifetime almost always drops, meaning the total decay rate goes up. But the real question you have to ask is, where is that energy actually going? Good Purcell enhancement funnels that energy into useful, radiative modes, giving you brighter emission. But bad Purcell enhancement, that just means the energy is rapidly bleeding non-radiatively into lossy metal modes. A shorter lifetime often just means the SPP is stealing your energy faster. Section 4. Defeating plasmonic loss. It's time to fight back. Let's move to and see how this builds into real-world performance gains. In a totally unoptimized state, a device might lose, say, 25% of its energy to SPPs, leaving an external quantum efficiency, or EQE, of just 25%. But by optimizing the orientation to be horizontal and tweaking the distance from the metal, we can crush that SPP loss down to just 10%. As a result, the useful light escaping to the air jumps up to 35%. Think about that. The molecule itself didn't magically get any better at creating photons. The device simply became vastly better at avoiding plasmonic loss. That's a huge win. To achieve those kinds of leaps in efficiency, engineers rely on this mitigation playbook. It's a systemic approach that balances molecular orientation, optical cavity design, and material selection. We can orient emitters horizontally. We can increase the emitter-metal distance by padding the transport layers. We can optimize the cavity thickness so the radiative modes are actually enhanced exactly where the emitters sit. We can swap out high-absorption metals for lower-loss ones like silver. We can even carve gratings to give the SPP that missing momentum boost we talked about earlier. Or, hey, replace the metal entirely with transparent dielectric mirrors. So the crucial point is, while there are a bunch of strategies out there, the absolute most direct structural changes an engineer can make are these three. 1. Orienting emitters horizontally drastically cuts off that TM polarized coupling. 2. Pushing the emission zone away from the metal literally suffocates the near-field overlap. And 3. Tuning the cavity thickness ensures that whatever light is generated is strongly favored to escape, rather than just coupling to the metal interface. Ultimately, understanding SPP coupling means recognizing it for exactly what it is: a sneaky process where an emitter loses its energy into a metal surface electromagnetic mode. Because vertical dipoles overlap so perfectly with those surface waves, engineering horizontal emitter orientations and optimizing layer distances are absolutely the most powerful levers we've got. They force the light out of the device, rather than letting it burn uselessly into the metal. Defeating SPP loss is just such a brilliant example of how fundamental physics and clever optical engineering work hand in hand. By visualizing these invisible traps, we can literally design our way around them. But it kind of leaves you wondering, right? As we keep pushing displays to be brighter, more efficient, and thinner than ever before, what other invisible quantum phenomena are operating right now inside the screens we look at every single day, just waiting to be outsmarted? Thank you so much for joining me for this explainer. Keep asking questions and keep exploring the incredible physics all around us.